Okay, so welcome everyone to our second HAO colloquium this week. So today's speaker is Qingyu Zhu, and he's currently assistant professor of physics at the University of Texas at Dallas, and he earned his PhD in physics from UT Arlington in 2020. That was after he did his Bachelor's of Science in Geophysics from University of Science and Technology of China in 2015. And he was a postdoc at UT Arlington from 2020 to 2021, and then he came here to HAO as ASP postdoc fellow from 2021 to 2023 before he moved to UT Dallas. And his current research focus on using data-driven modeling to investigate the interhemispheric asymmetry in the storm time magnetosphere, ionosphere, thermosphere coupling. Today he will talk about that very subject. So go ahead.
All right, thank you, Nick. So hello everyone. So it's always great to come back. So at this time, because this time is before the time the Texas is getting hot. So I know I'm sorry I can't make it yesterday because I need to upload 200 students for their final grade. So it's a Texas one I produce. So today, let's just focus on the hemispheric differences in the storm time ionospheric and thermospheric responses to the traveling and atmospheric disturbances. So we know the Earth is significantly covered with the magnetosphere, forming the electric circuit at high altitude. So there are region 1, region 2 currents flowing from the downside to the dark side on the two sides, and in between there are also current flow in the ionosphere that try to close this circuit. So because ionosphere is a weak conductor, so with current, there will be heating, and such heating is called jaw heating. So, and during the storm times, tremendous jaw heating can be deposited into thermosphere and ionosphere, and which just, well, if you imagine it as a falling rock, it's just falling into the pond, you will see rivers propagating away from the source region. And this we call the traveling atmosphere disturbances, TADs. So the heating, jaw heating mostly deposit on the down and dark side. So, and which can just exhibit variations. And there are also significant differences between different hemispheres. So here just shows the simulation output for one time. So during the 2013 Patrick Day storm in the northern and southern hemispheres. Well, several factors may contribute to these interhemispheric symmetries. The first one is the IMF clock angle, which we will mainly focus on today. And the second one is the season. The third one is the different configurations of our magnetic field in different hemispheres. So there are also some open questions. As first, can the TADs, well, we know the jaw heating can be different. The first question is, can the TADs, characteristics of TADs differs between different hemispheres? If so, how do they differ between different hemispheres? The second one is, well, we know TADs can cause the ionosphere, thermosphere effects. So how do the interhemispheric symmetries in the TADs also contribute to the interhemispheric symmetries in the ITCs? So today we will just use maybe a couple of case studies to just try to answer these two questions. So the first one is it's just the interhemisphere. We focused on the thermosphere. So we mainly focused on the interhemispheric symmetries at high altitude neutral density variations during a storm that occurs around the March equinox in 2022. So, well, as mentioned earlier, so IMF-BY, the clock angle can play an important role in just causing the interhemispheric symmetries in the high altitude neutral density. So on the right shows some the statistical results from the data. So what you can see there's some interhemispheric differences in the hotspot on the curve, which is highlighted by the red arrows, and also the locations and the density, the locations and magnitude of the low density cell. So So these are just from the statistical data, and those characteristics can also be well reproduced by the simulations when reaching the static equilibrium. But the question is, so these interhemispheric symmetries either just derived from the data just observed from a wide range of geophysical conditions, or the simulations reaching the steady state. So, which is sort of a steady case. But the question is, how do the interhemispheric symmetry? How does the interhemispheric symmetries in the high energy density look like when we just approach it from a dynamic perspective? So we will use this event to do the study. So this study will be approached by a combination of data analysis and numeric simulations. The model we are using is called Global Ionosphere Thermosphere model, which is a three-dimensional GCM for the upper atmosphere. It's non-hydrostatic. So in this situation, we see in this study, the datum is coupled with the NCAR 3 dynamo, which was developed by Atrid and Art maybe a couple of years ago, maybe 10 years ago. So, and we in this study we also use realistic ampere field current to drive the model, and the aurora presentation here used is sort of empirical. It just from the patterns given by the model called Ashley, which stands for the aurora spectral and high magnitude electric field variability. We also utilize several data sets. The first one for the validations, the first one is a DMSB high latitude cross-track ion drift. We also use the neutral density from measurement from the grass follow-on and swarm satellite. Both of them are derived by the high resolution accelerometers. So what the Ashley stand for here, just a brief introduction for the Ashley model. So Ashley has three components. All of them are derived from the DMSB measurements. So specifically for the Ashley A, which A stands for the aurora. So it actually can provide the differential energy fluxes in the 19 energy channels measured by the DMSP under different geophysical conditions. So one improvement is it can just improve the soft electron precipitation part, which is mostly the energy below 1 keV electrons. So you have seen that there will be two orders of magnitude differences for the 100 around 100 eV. We will also use Ashley E, so later on. So Ashley E is improved model, provide the potential patterns, average potential patterns at high latitudes. So which is similar to the Weimar potential model. So here is a summary of this the geophysical condition during this event, along with several dynamic outputs from the datum. So this event is so the minimum DST reached a little bit below minus 100 nanoturns. During this event, it has several southward IMF turnings. So 3 actually. So and what we will focus on is the one highlighted, which is during the second turning of the IMF BZ. So, and during these turnings, BY is also very important. It's mostly negative and is comparable with the BZ. So, and also because of 3 southward IMF turning, so you can see 3 elevated field line current period with elevated field line current. And bottom 3 panels shows the cross-polar cap potential, hemispheric integrated joule heating, and or electron precipitation called hemispheric power. So during the second one, although you can see the field line current and the cross-polar cap potential is comparable in the northern and southern hemisphere, there's a significant difference in the joule heating. So the northern hemisphere roughly 50% higher in the northern hemisphere as compared with the southern hemisphere. So, and on the right shows the distributions of the electric potential, the electron precipitation flux as well as the Joule heating. So from the bottom row, you can see the Joule heating is distributions and magnitude are pretty different from the different hemispheres. So here we just try to do some validations for the model outputs. So first, we focus on the DMSP high latitude drift. So red lines is from the simulation, and the black dots are from the observations. So basically, the Filler current driven GTEM simulations will reproduce the high latitude ion drift. On the bottom, we shows the comparisons with respect to the neutral density measurements. So again, the red line is from the simulation, black line is from the observation. So again, we can say that GTEM simulations also will reproduce the observation to a large extent. Especially, we'll focus on these two spikes, level and spike 1 and spike 2. Spike 1 is observed in the northern hemisphere, which it has a much higher magnitude. Spike 2 is observed in the southern hemisphere, which is relatively weaker compared with the spike 1. So the reason why we need to use the Filler current to drive GTEM is because here is a slide to highlight the necessities of using the realistic forcing. So we here, in addition to the red line, we also add another green line here. So which is both simulations are driven using the same precipitation patterns, but the way we specify the electric potential patterns is different. The red line is with Filler current driven simulation, and the green line, we use the empirical HDE, so which we basically use an empirical potential model to drive the model to drive GTEM. So as compared with the red line, you can clearly see that the green line here, it can't well reproduce those spikes. So especially the two spikes labeled by those pink arrows. So, and here just shows the neutral mass density from GTEM as well as the Joule heating in both northern hemisphere and southern hemisphere before and after the identifications of those two density spikes. So for the spike 1, so for spike 1, you can see that the spikes is propagating structures originally from the downside and propagating to the dark side. And for the spike 2, the propagation is it's also propagating structures, but the propagation directions is pretty different from the northern hemisphere one, and also the magnitude from the for the northern hemisphere spike is much stronger than the southern hemisphere one, and also the spikes. So especially when the satellite identifies those spikes, it doesn't co-locate with very significant Joule heating input. So suggesting it's probably not generated by in situ heating here. So this is this figures just tells us. So, and we also try to validate the Thermosphere outputs just from a different way. So here, as you can see, so the spikes, so those propagating structures on the northern hemisphere, one is propagating around the 6 to 18 local time sectors. The other is sort of just propagating from the 3 to 15 solar time sector. So we just try to investigate their propagations properties along these two directions in the northern and southern hemisphere respectively. So we use the Mariana wind because we actually have some Mariana wind measurements and lower latitudes. So here, so for the one corresponding to the spikes, so this PAD is sort of we label it as T1. But in addition to this transformer one, we also have the equator one propagating TADs. We label it as T3. And T2 is the one just propagating cross-polarly in the southern hemisphere. And there's also equator propagating TAD. We label it T3, T4. And T4 and T3 actually can be observed by the Icon satellite at lower latitudes. So which gives us a little bit more confidence that the T1 and T2 are maybe more realistic. And additionally, you can see that T1 is, in addition to much stronger, the phase speed is actually higher than the T2. So the phase speed for T1 is about 1,000 meters per second, while for T2 is about 700 meters per second. And also the dissipations for T1 is much slower than T2. So T1 can reach almost to the equator, while the T2 just dissipates somewhere between -30 to -60 geographic latitude. So, and then we actually try to see whether T3, T1 can just propagate and T2 can propagate those far away from the region, the source region. So we just expand the time frame we are looking at. So this is the time when we just identify the T1. And then after another trajectory, we also found a spike here, so which corresponding to the same propagating structures at when it propagates to the lower latitudes. So suggesting that the T1 is at least realistic. So, but for T2, unfortunately, we didn't really detect very significant structures up another rotation. So it's possible that the dissipation of T2 is much faster than that is predicted by our GitHub simulations. So this is the also some differences in the TADs just triggered in the northern and southern hemispheres. So to sum up for this part, so we found that, well, GitHub well captures the intense polar caps density spikes at high latitude. And also we also just did some detailed analysis for the neutral density enhancement structures associated with Q spikes. So, and we found those spikes are just caused by the transporter TADs, and those TADs can have some exhibit very significant in hemisphere symmetries. And this provide and this polar cap spikes is definitely not well captured by the patterns that we derive from the static or the steady perspective. So providing suggesting that it's important to understanding the high latitude neutral density responses from a more dynamic perspective. So this is the first part.
Actually,
Yeah.
ask a question.
Sure.
Yeah, so you mentioned that for the northern hemisphere TAD, it's not correlated with where like the hydraulic heating occurs, and it's because of local heating, right? What's the mechanism there?
So these spikes. So typically when we assume there's enhancement, we assume there's a heating correlated with it.
Yeah.
But this spike is just caused by so initially the heating source is on the downside, and these TADs propagate toward to the polar cap and cause a spike there. So it's not co-located with the same the heating at the same locations, but it's caused by the heating from a remote location.
How they connect? Is it just you not observe them simultaneously, or is still attributed to the geoheating of the other locations?
Well, from the simulation, we can attribute to the different locations, but in the observation, it's very challenging to.
Oh, okay.
Yeah.
You mean in observation, you cannot.
Right, because the swarm can't measure the electric field at the same. The precipitation and the electric field at the same time. So
Is that observation or
this is a simulation.
this is simulation?
Yeah, we only observe the density structures along this path. So there's two paths. That's the observation.
But in simulation, you do see it's originated there and then.
Right. Yeah. Right. So from here, so this is the heating that corresponding to the TAD generations.
Oh,
TAD is here, then here, so you can see it moves more towards the dark side.
okay, I see, that makes sense.
Right.
Thank you.
So I have a lot of questions on the model setup, but I will defer to the end of it.
So from this part, we have know that the TAD can propagate to the low latitude. So, and we have ERAs as lower latitude. So this part, which is actually the first project I did when I was a postdoc here. So we're focused on the interhemispheric thermometries of the ERA due to the TADs during a well-known Sagittarius Day event. So we will mainly focus on the ERA and in the American sector here. So this storm, occurs more than 12 years ago. So it's a storm that triggered by a CME. So it's actually minimum CMH, it reaches below 100 nanotesla. So it's also an intense geomagnetic storm. So this storm undergoes two-step growth. You can see there's a slight recovery of the CMH here, and then has another intensifications. So we will mainly focus on the ERA response in variations during the second intensification. So what the motivation for this study? So mainly because that, we actually noticed there are negative phase occurs in the southern hemisphere. So, and also the negative phase in the southern hemisphere is much stronger than that in the northern hemisphere. So then, we try to understand why there's interhemispheric symmetries in the negative storm effects. So here the figure only shows the absolute values, but we also check the relative differences. It's also stronger in the southern hemisphere. So we just integrate the model simulations with the data analysis. The data we use is the ground-based GNS TC data. And the model again is a GETM. So this time, instead of using the field current, we will directly use the AMI patterns, the patterns derived from the AMI technique to drive the GETM. So AMI stands for the asymmetric mapping of the ionospheric electrodynamics. So it just provides optimal estimations for the high latitude electrodynamic field based on a variety of measurements, including the ground-based magnetic perturbations, satellite-based horizontal magnetic perturbations, DMSB, cross-track, ion drift, super-down measurements, and also the SUSY electron precipitation for generating the patterns used for this study. So first, we try to validate whether our GETM simulations will reproduce the observations. So clearly, we found there's two blue regions around the ERA peaks, and also the blue area in the southern hemisphere is definitely more deeper than the northern one. So this is give us a good start for this study. So, and then we try to understand whether the TAD is the major contributors for the ERA variation, for this study. So then we start from the term analysis. So the variations of the electron density just as a combination of the chemical reactions, transport processes of the equal-speed drift, neutral wind, and the antipolar diffusions. And indeed, we found that the variations of the transport of neutral wind is mostly resemble to that of the left term, the term on the left-hand side. So suggesting that the neutral wind transport is a very important process for causing the variations at the ERA region. So, and clearly, so from the simulation, you can see there are some oscillations in the neutral wind suggesting the existence of the TAD. So, and at the time we are looking at here is the around 16 UT of this time. So the neutral wind is poleward, so it's southward, which and the southern hemisphere, which suggesting the neutral wind is poleward. So for a poleward neutral wind, so well above the peak height, it just brings the ions downward along the magnetic field line, so to a region that has higher recombination, reducing the electron density there. But below the HP, the F2B, so the neutral wind tend to compress the ionospheric, the ionosphere, so actually increasing the electron density below the roughly at the region most below the peak height. So this suggests that the meridional wind, together with the vertical shear of the meridional wind, contribute to the negative effect. And the vice versa is true when we have a equatorward neutral wind. So, so from here, we try to see whether there are significant differences in the neutral wind at conjugate locations. One is negative 15 degrees, the other is positive 15 degrees, which roughly co-located with the EI peak locations. So as you can see that the neutral wind, the colors for the neutral wind is definitely not as significant in the northern hemisphere as compared with the southern hemisphere, suggesting that disturbance winds are stronger in the southern hemisphere. Then the question is why? So here we know there are a lot of TADs happening here, but we highlight two TADs that mostly responsible for the TADs on the left. So the TADs, well, as you can see, the generations, propagations, interactions are pretty different in the northern and southern hemispheres. And the one part is the TADs in the southern hemispheres are generally slower in terms of the first speed, is that those triggered in the northern hemisphere. Therefore, although the TADs interact, two TADs interact exactly about around the 15 degrees south in terms of magnetic latitude, the TADs, well, of these two interact actually equatorward of the positive 15 degree latitude. So leaving the neutral wind disturbances at northern hemisphere is weaker than that in the southern hemisphere. So, and the reason again, so we take a look at the jaw heating at the source region, and we found that the neutral wind in the jaw heating in the northern hemisphere, which at this longitude is mostly stronger than that in the southern hemisphere. So this just explains why the TAD's fast speed is generally higher in the northern hemisphere, probably due to the stronger jaw heating in the northern hemisphere. So, well, again, for this study, so we mainly focus on the ionospheric response at American sectors, and we found the TADs are most important for the ionospheric response for this storm. And the asymmetric negative storm effect also mainly attribute to the differences in the TAD properties and their interactions in the different hemispheres. So this is the for this study. So this is one example that shows how the interhemispheric symmetries in the TAD affect the response of the ionospheric response to the storm. All right. So for the previous two events, we focus on the storms that occurs very close to the equinox. So let's further talk about one storm that more close to the solstice. So this is mainly done by the undergraduate student who worked with me last summer, so at UT Dallas. So this storm, so for this event, one of the features that most attracted us is that, so the TAD is actually much stronger in the northern hemisphere, which is expected But there are still something triggered in the southern hemisphere, although much weaker. The one thing that is very interesting is that the northern hemisphere TIDs reaches to the geomagnetic equator, while the southern hemisphere TIDs only reach about -30 magnetic latitude. So, well, there's several possibilities. One, whether the phase speed has very significant difference between different hemispheres. Two, whether the locations that trigger the southern hemisphere TIDs are just further away from the equator.
Is this a GPS-TC?
Yes, this is GPS-TC. The third one is whether well, we want to understand the linkage between the interhemispheric symmetries in the TIDs that contribute to those TIDs associated with the interhemispheric symmetries in the geoheat. So these TIDs are actually just caused by the energy just deposited in the initial phase of this storm. It's not even reached the main phase of the storm, but you can still see very significant impact here. So again, we use the Freelike current to drive the model here. So everything is very similar to the first part of this study. So the first step again is just using try to validate whether the high latitude estimation is reasonable. Again, we compare with the DMSP measurements. So and we found that the high latitude altitude is well reproduced here during the initial phase. And also here we just try to see what's the significant interhemispheric symmetries in the high latitude parameters. So we compare the field current, the cross-polar cap potential as well as the hemispheric integrated geoheating. So well, we know that because this is close to the summer solstice, the field current is definitely higher in the northern hemisphere than the southern hemisphere, about well, maybe a square root of 2 here. And also, but the CP is rather, the cross-polar cap potential is rather comparable in the northern and southern hemisphere. And for the geoheating, so roughly the northern hemisphere is roughly 2 times of the southern hemisphere. So this is time variations of those parameters. And here on the left shows the distributions of the electric potential as well as the geoheating at around 20 UT when we see the maximum differences between the geoheating in the northern and southern hemisphere. So clearly the distributions of the geoheating along with their magnitude are quite different. So again, the magenta now highlight the 75 west degree in terms of longitude. Yes.
Question.
Sure.
So you said that the potential drop almost the same between two hemispheres, and then your aurora precipitation is the same
Right.
from the same model. So
Right.
why the geoheating has such a big difference?
I think that's probably the distributions of the potentials. Yeah. So the CPCP can reflect the electric field.
How do you derive the CPCP?
That's well, the maximum minus the minimum.
Okay, from the
Is the potential output. Yeah.
Okay.
So again, we try to validate whether we do well capture the TIDs during this event. Well, although there might be some differences, but we do we do at least capture those 3 bands, the blue, red, blue here. So you can roughly correlate it with the simulated TIDs. There are also some TIDs from the southern hemisphere, although the magnitude is indeed weaker in the southern hemisphere. And we also, well, because at this longitude, so we also, this storm, the gauge daylight is around its measurement is available. So we also see whether we do capture the TADs, the thermospheric disturbances roughly at the same time. And well, again, we find we are able to capture the thermospheric disturbances simultaneously. So, and then we try to determine the phase speed of the TADs during this event. So here we show the meridional wind here to help us to determine the TADs. And on the contour here just shows the jaw heating that triggers those TAD or TIDs. So, well, we found the phase speed in both northern hemisphere and southern hemisphere is roughly the same, around 900 meters per second. The locations with respect to the geomagnetic equator is also roughly the same. Well, maybe this is a little bit the locations we don't know. The locations probably is further from the northern hemisphere, but the TADs in the northern hemisphere seems triggered about 1 hour earlier than that in the southern hemisphere. And also the TADs in the northern hemisphere is much stronger and dissipated more slowly than the southern hemisphere. This is probably because the heating is stronger, and this is the background is also strong. So the disturbance is also strong here. So here we try to see why the northern hemisphere, the southern hemisphere trigger the TADs roughly about 1 hour away, 1 hour after than that in the northern hemisphere. So here we just try to we just replace this neutral density by the meridional wind, just following the format in the part 1. So the top 2 panels suggest the one from the northern hemisphere, bottom 2 from the southern hemisphere. So the TADs triggered in the northern hemisphere roughly corresponding to the heating deposit about at around the same longitude, while you can see this low heatings deposit in the southern hemisphere at this time. But about 1 hour later, so you will see there are some heatings finally deposited at this longitude, and that triggers the TAD or TIDs that from the southern hemisphere. So the different behaviors between the northern hemisphere and the southern hemisphere TAD or TIDs is probably because the time difference of jaw heating between the northern hemisphere and southern hemisphere. So this is the study that directly just compare the different properties of the TAD or TIDs in the northern and southern hemisphere, and we also try to understand the underlying linkage between the properties of the TAD or TID and the jaw heating. So the bottom line is the northern. So we try to focus on the phenomenon why the northern hemisphere TADs trigger about 1 hour earlier than that southern hemisphere. This is because, well, when the northern hemisphere TAD is triggered, there's no jaw heating deposit at the same longitude in the southern hemisphere. So, well, this probably suggests that the RMBY along with the season may just lead to this significant inter-hemispheric symmetries in the jaw heat. So I think the overall story I want to just share with today is that the interhemispheric symmetries in the jaw heating can lead to different generations, propagations, and interactions of the TADs between different hemispheres. And those interhemispheric symmetries in the TADs can effectively cause the interhemispheric symmetries in the ionosphere and thermosphere response to geomagnetic storms. And with that, I'll stop here and happy to take questions. Thank you for your time.
Thank you. Any questions?
Yeah. I have quite a lot of questions, but one of them is that which version of the 3 dynamo model are you using?
That's probably the very early version of the
So that comes my next question. In the very early version of the 3 nano model, it doesn't deal with the asymmetric high latitude inputs.
I do some modifications.
So you apply some basically some overlapping of the potentials or some other.
No, I calculate loss first and the solvent first. I calculate twice. So
okay, which means then that essentially means since the original 3 nano model is a folded hemisphere, so that means you are basically dividing the hemisphere input into 2 hemisphere and solve that and add two.
No, so when you do the calculations, so you just, instead of summing the northern hemisphere, southern hemisphere together, you sum up northern twice, sum up southern twice for the calculation. So this is, you can do some modifications in the calculation.
Okay, that can really explains why you got different potential in 2 hemispheres. And the next thing is, does that did what you mentioned is you add up things, calculate things twice. Does that lead to artificial interhemispheric asymmetry?
Well, so we validated with the DMSP variance.
Okay, no. I mean, even if you compare with DMSP measurement, it doesn't really resolve your physical consistency, whether it is the true interhemispheric asymmetry or it's just some artificial manipulation that leads to better data model comparison.
So you use field current from the northern hemisphere to calculate potential in the northern hemisphere, using the southern hemisphere field current to calculate southern hemisphere potential. So why it causes the artificial interhemispheric asymmetry?
I mean, the current system flows from the one hemisphere to the other hemisphere.
Right. Yeah. So we assume that's probably below a certain latitudes. Above that certain latitude, we just assume they are separate things.
Okay, that will work. Although I'm not convinced about that. Yeah, that's. Oh, the last thing is in your previous slide, I don't really see a lot of interhemispheric symmetry there, though. In your model simulation, that's pretty symmetric.
Which one?
Just the next slide. I mean, from
this one.
Yes, this one I would say it's pretty symmetric in 2 hemispheres.
Well, so yeah, so I just so this one, so this is pretty symmetric in terms of the phase speed, but the timing is symmetric. It's asymmetric between the different hemispheres. So the one in the northern hemisphere occurs a little bit earlier than the one in the southern hemisphere.
Oh, okay.
Maybe I understood wrong.
Yeah.
I saw that the older dynamo is to 3 times, not 2 times. First is the average northern southern
Right,
you
right.
get symmetric. And
Yeah.
then you got global solver.
Yeah, right.
Then you add the asymmetry part,
Right.
basically subtract that, then do twice, one for northern polar region and one for southern
Right,
polar
yeah.
region, then fold it together.
Yeah,
So
right.
it's 3 times.
Yeah, the only the 3, so I changed it to 2. Yeah.
Oh, you changed it.
Right.
Any other questions?
You compare your kitten with some situ measurements. How high is your kitten top level?
So for example, for the first one, so because it's a curve, it's about the solar F10.7 is about 120. So the maximum probably 600. So
600.
the second one is for the 470 something. Yeah.
Okay.
So why the phase speed about it's the same? You know, they start the solstice conditions. So usually the phase speed is the local sun speed.
Right. Yeah.
For JD. So why so the northern southern here I would expect it much different than
Yeah.
the
So
space.
Right. Yeah.
different space speed.
Yeah. So this is something I originally also see maybe the summer has a higher per day is a fast speed than the winter one, but from this two line, it's just keep the probably the background thing.
It's on that, how symmetrical is supposed to be.
Well, basically roughly proportional to the local sun speed. So if you have a solstice condition, one hemisphere temperature, thermal temperature, neutral temperature is much higher than the other. So you will see that one hemisphere is faster than the other.
Yeah, that's understandable. I'm curious, like quantitatively, because like this estimation also has some uncertainty. Was that also?
Yeah, but how-
the uncertainty can be like a magnitude.
Well, okay, it just depends. I think that the solstice conditions, the temperature is a several hundred degree difference between the two hemispheres. It can be 70 It's a square root of
Square root,
temperature, yes. So, but the uncertainty also arises, how do you draw your dashed line?
Right. Yeah. But there's no significant like
Yeah.
no, not 50% or anything.
Yeah, this one has some uncertainty rate.
Yeah.
This one is the big. But yeah, even if like it's a 50% difference, then you do a square root, it's like a 20%.
Yeah.
I think this inclination estimate can easily have like 20%.
Any other question? No? Thank you again.
All right. Thank you.